So yeah, I'm Tom from the Software Architecture Group in Potsdam, and we're going to talk about partial parsing for structured editors. So the domain structured editing has been well explored. So I assume most of you know about it, but very briefly, the idea of editing code on a structure level rather than a textual level. So if this up here would be your abstract syntax tree, this might be a representation of a structured editor where you can see these sort of HT nodes got turned into these blocks, right? And Blockly, of course, which we just saw another incarnation of this. In particular, in prior work, we have seen some very desirable aspects about these structured editors. For one, that adding natural keyboard-based interactions is possible in structured editors, but in prior work usually required some degree of effort, varied depending on the types of interactions and types of frameworks you were using. And secondly, that generating structured editors from grammars is possible automatically. And in this work, we are aiming to put both of these parts together to create structured editors that have natural keyboard interactions built in. So when we say natural keyboard input, what we mean in this instance is to have keyboard input with the goal of providing people with a lower entry barrier, because they already know it from textual editing potentially, and possibly also with a higher efficiency, because you don't have that viscosity of interacting with menu-based structured editors. Note, however, that this particular work, this partial parser aspect, is only the very first puzzle piece in achieving this goal, because it is really constrained to entering expressions from left to right, so similar in the way I suppose the parser would take them in, as we'll see in a couple moments. So this figure down here kind of paints the picture where we want to be at in the end. You can see here you are maybe a Java-like language, which in turn is parsed and turned into this sort of HT, and gets represented in this structured editor back here. You can see the cursor, the various elements that are editable, etc. So then, if the user provides a new input, such as this plus sign, what we want to be able to do is recognize that their most likely intent would be to turn this 2 into an addition, a 2 plus something. So we can see here that this node was taken in isolation. We analyzed it through the partial parser, we'll get to that in a moment, found that indeed this can be done, and turned it into this expression 2 plus something, in this case like a whole waiting for an expression to be entered. And finally, mounting this new modified subtree that incorporates both the existing selection and the user's input back into the structures editor editing model. So this is where we kind of want to end up at. I said that we are doing this starting from a grammar. In fact, there's no particular requirements that this partial parser requires your grammar to have. However, in prior work, we've seen that the closer your grammar is to the way that people think about a programming language, the better the mapping is going to be if it's done automatically. So for our work here, we've chosen the tree-sitter grammar formalism as the basis, because it carries a couple of desirable properties for us. For one, explicit precedence and associativity, has an inlining concept, and it also has a large number of grammars readily available for all sorts of mainstream and even lesser mainstream languages. Down here on the bottom left, I've brought a little example of the tree-sitter domain-specific language, which is embedded in JavaScript. You can see here in particular we have these super types, and we've marked expression as such a super type, which essentially just means that whenever we encounter an expression, our concrete syntax or parse tree rather, we do not need to display it, but rather we directly move to one of its subtypes. So we only have this add node, not an expression, with a child of an add node. Down here you can see the associativity. In this case, all of these are left associative, and also numbered precedence. For comparison, and also because we're going to use this grammar as our running example, I've also pasted it here on the right-hand side in a maybe more familiar style. You can see in particular that it's an expression-based grammar with like this ID rule, constructor, addition, multiplication, and a potentially JavaScript-inspired closure expression here. All right, so given an input such as the character n and an unmodified parser for this grammar here, what would it return? Well, most likely, and by all implementations, just the ID parse node with just that letter. This is the exact singular tree that we can form given the regular parsing algorithm. For the partial parser, contrarily, we want these 5 results. And how we get there, we will see through the first 2 steps, and then the last 3 secondary concerns that are also relevant for this implementation. So it's mostly going to be allowing incomplete sequences to still produce a valid parse tree. All right, so let's look at the first step. Assume the example, again, we get the n as an input. We start from the expression, and we're exploring all the options, as it usually does in a top-down manner, and we're expanding the addition here, expression plus expression, finds that ID can be done, and indeed the n can be consumed by the ID node. Normally, we would abort here unsuccessfully because this add expression cannot be completed with just this input. It needs the plus and another expression to proceed. However, this is where we tweak the logic of the parser and instead allow it to autocomplete the sequence because it has been started. So had nothing matched, we would have also just discarded it. But because at least one element did match, we are allowing it to autocomplete. What does that autocompletion look like? Well, for a terminal, it's quite simple. We just literally take the terminal, and for a non-terminal, you can probably guess it. We saw at the start, we just place a hole there, allowing the user to auto-type something in there later on. So this allows us already to complete a whole set of expressions that are a little more complex. And the next step is to extend this to regexes or literal labels inside of your grammar. So again, the same input, an n. We are exploring the new node, and we realize, okay, we can take the n of it, but then there's something missing. We can't match the entire string. So how we modify this here is that we allow the regex or the string to prefix match. And if there is a matching prefix, we allow it to autocomplete yet again. In this case, it's easy because it's a label, so we can just take the entire new and move on. For regexes, it's obviously a bit more difficult, so we usually just take the input that is there. But we've also experimented a bit with analyzing the regex and seeing if it makes sense, like, for example, if it has a literal suffix or something like that. And then, yeah, we just autocomplete the terminal or the matched value for the regex and proceed with the sequence that was wrapping this constructor as before by adding a whole expression here at the end. All right, so with this, we already got the essential ingredient, which is basically that our partial parser is now allowing people to commence typing an expression, but instead of rejecting it, it will expect and enumerate all possible continuations of that input. At the start, I showed you these 5 results as the desirable output, but I sort of lied to you because maybe you already had a hunch that this wasn't actually the best possible answer you could get here. In particular, these 3 in the middle are feeling sort of repetitive given the first one. And indeed, in our sort of work analyzing how this works and how we felt about using it, we eventually settled on only producing these 2 entries as the actual output. Why these 2? Well, they have as a prefix node, not just as a prefix string, one of our other results. So the procedure in which we are minimizing the trees is by grouping them, by checking if any of the nodes that we found can act as a prefix for another node. And by this measure forming groups, and then taking the minimal one of that group as a potential result. The logic behind, or the intuition rather, behind this is also probably quite clear, because if you have an ID node, it is rather trivial for the user to just continue typing by entering the plus and then turning it into an add node. Whereas for the new down here, it's actually a completely different language construct. It has nothing to do with an ID node. So these are sort of 2 different things clashing here. The next concern is sort of orthogonal to these sort of things, but carries some very nice properties. Namely, because we are doing this in this sort of continuation manner, it is very easy for us, similar to an incremental parser, to reuse existing subtrees. So this has two benefits. The obvious one, we get improved performance, such as in incremental parsers, but also that nodes get to keep their identity while the user edits them, which is, of course, good if you're trying to build tools, as you often do in structural editors. So what does this look like? Well, if we have the cursor of the user here behind this multiplication expression, and the user enters a plus sign, the input that we're feeding to the parser is this existing AST node, multiplication 2 times 3, not as a string, but literally as the node, and adding the plus as a string input. So the only change that we need to do for this is to adapt the way that our non-terminals are processed. If they see that the next thing that is in the input stream is a symbol, it tries to match its type, and if they match, it just literally takes that existing subtree and puts a reference of it into the output. And otherwise, it just continues expanding its tree normally. All right. And the last concern is around left recursion. Let's change the grammar that we've just seen and take this example, which is a little more convoluted and maybe constructed here. So what we have is, again, an expression rule that can expand to an add, an increment, and a number rule. And you can see here, these are the typical postfix, increment, and binary addition. And we assume that postfix increment binds more strongly than this binary expression up here. So now if you take this example up here, 1 plus 2 plus 3, and we have the input plus, what our algorithm, unchanged as it is, would actually sort of commit to this local optimum as early as possible, because just given this selected node and the input plus, we realize, okay, there's one rule that exactly does this, that's this one, and it also happens to bind the most strongly, so it's just valid here and we're good to go. But intuitively, as the user, you would likely realize that entering a plus in this sort of expression is very much unlikely to be your desire to increment that number here, because that wouldn't even work in most languages. So what we actually want to do is to consider both our results and those of all of our left recursive parents. So if we do that, what we get is two different options that could be completed here. For one, the update expression that we already got previously, but also this slightly larger expression here where we can continue typing our binary addition. All right. So with those pieces, we got what we are currently running under the name partial parser complete. And what it does is essentially approximating the work of a normal parser for partial or in progress input, while continuously providing feedback by eagerly committing to options. So the user is typing, and rather than waiting for them to complete a valid statement, which is probably the naive way to do the same thing, we're committing as early as possible to things that we already know, or at least we're presenting the user with all available options at this point, such that they either benefit from the guidance or can just confirm these sort of act like an auto-completion menu that you can just click on at that point. All right. So we evaluated this work through an experiment. In particular, we sourced single line changes from popular Git repositories, open source ones. So we used Flask, which is written in Python, Express.js, a server framework, again, same as Flask, which is written in JavaScript, and Overtone, like a live coding closure library. And in particular, we looked for single line changes in order to approximate sort of realistic inputs that users would have given throughout the evolution of the respective software packages. Once we found these sort of changes in the diffs of the most recent commits of these projects, we found the closest parent in the AST that contained the entire change, changed that node into a whole, and then literally a character by character retyped the AST node as it was. If this then results in the same AST as before we did the change, our partial parser behaved correctly in that instance. And we did this for the first 30 single line changes that we found in each project, so totaling up to 90 changes. You can see one example of a single line change of our corpus here. That is this mock.uri.params equals mock.uri.params or empty object in JavaScript. And that would also be the literal string that we would feed to our partial parser to see if it is able to reconstruct it. So there was one class of failures that occurred, which I think amounted to 5 failures. It's written in the paper as well, all with the same language construct. So what happened here is that this was what we wanted to type. This is the literal input that our partial parser received. And you can see here sort of the sequence of how it interpreted this. So as soon as we typed the from, this was the what you see in the first row, what it auto-completed to. So it already contained the import because this is syntactically required, right? So once we type name, everything is still great. But then we start typing the second keyword, leading to the fact that we insert this I over here rather than recognizing, indeed, this belongs to the keyword, because there's no real manner of distinguishing these at this point. This is obviously a deficiency in the way the algorithm works and might trump a user's muscle memory. So it is something we're investigating fixing at the moment. But of course, this is not deal-breaking in the sense that it would have been easy for the user to recognize this issue and tap over. They might have even preferred it or gotten used to it. But obviously, this is not something that should stay in this approach. Taking that same experiment, we also analyzed the performance of our system. In particular, every time we simulated a keystroke, up until the point where the minimized result set was available, we took the time, which amounted to a total of 1,233 queries to our partial parser. The highest measured value of response time was 0.1 milliseconds, so well below what interactivity requires, since this only happens on every keystroke on top of this. So that should not be an issue. With the grammars that we tested, which, as I showed earlier, was the Python, JavaScript, and Clojure grammars. The length of the inputs, median was around 30. Oh, that's back here. And we also noted that the fact that we reused the nodes had as an impact that a lot of the changes were in the very small area. So this basically, if that's not entirely clear, we, for every query that we started the parser with, we just took the length of the input stream. So if there's an entire node in there, it would also just count as one, since in the end it's also nothing more than just a simple comparison. So this fact that we reused entire nodes skewed our results to be more to the left here. And the ones that are on the very extreme were usually just like entire strings where our system was waiting for the quotation mark to finally appear, or similar things. All right, so considering related work of this, there are a couple of approaches that accept incomplete input, which are grouped here at the top. First one, probably the most similar to our approach, is substring parsing, which has many of the same goals, except, at least the way we read it, the one for exhaustiveness, which means that, again, the way we understood it, the substring parsing approaches have as a goal to support the user rather than be the only and ultimate means to enter input, which is indeed what our partial parser aims to do. And it as such has higher requirements on correctness, because if it doesn't work, you literally can't enter this language construct, where substring parsing has as a fallback textual editing and similar means. Next up, error recovery. Also some related aspects, but obviously not trying to resume parsing, but rather to contain errors. Similarly, island parsing, which is skipping sections of input that are not of interest and limiting the parse results to those, but again, slightly different to what we are doing. I already mentioned incremental parsing, which as a goal has to speed up by reusing subtrees, but is also not aiming for partial results. Then in a different group of related work, we have works such as Rascal to MPS and Kogi, which are taking grammars and mapping them to keyboard interactions. And finally, Grammar Cells and Barista, both works which have structured editors, which are very excellent for providing keyboard input, but require these handwritten specifications. Do you still have time for the future work, or should we move on to the questions? Yeah.
Please come to an end, yeah, slowly.
Yeah, all right. So yeah, in terms of the future work, the one most obvious one is probably here in terms of the skipping of already completed keywords. We have a couple of cases where prefixes post issues, for example, integers and floats share the same prefix in the Python grammar. And finally, probably the most obvious one, this does not present a complete editing system, and extending it to this is the next step that we'll be taking in this work. All right, so thanks for your attention, and I'll be happy to take questions.
Do we have any questions in the room? Yeah. I can repeat the question.
Let's see if this works.
It is.
So, yes. So I think first I have a very quick comment that you mentioned you also like to do some auto-completion, because I also find it very useful when you mention the example, like when the user types n, it can be the identifier, or it can be a new keyword, or it can be more options, right, in the grammar. So which means if you have a auto-completion list, it's much easier for the user to simply choose one of them so that he can type the code much faster. And then I have a question is regarding your parsing algorithm, because you didn't mention, I'm curious whether you are using, let's say, some LL or AR parsing, or using some other parsing algorithms you propose for this kind of problem.
Yeah, so our partial parser is based on a top-down parser that re-implements the most part of the tree-setter parsing logic, which is essentially just a CFG parser, which I think works with the parsing table as in their implementation, but we changed it to act top-down in order to be able to decide more flexibly on the routes we're taking, especially during experimentation, if that makes sense. For left recursion, we use the seed growing approach that is also used in some other parsing implementations.
All right. Could we switch over to the next speaker and maybe take one more question? Do we have another question? All right. Thank you, Tom, for your talk.